Suppose there's no such thing as gravity, and I stand at the top of a 125-meter high cliff and I drop a ball. It's gonna hover there and do nothing, right? Of course, if there is gravity, it's going to fall, which you can see here in real time. We can grab the distance formula, simplify it down, and then calculate how far it falls or how high up it is. You should know by now that if we round g to 10 meters per second squared, the distance an object falls each second is 5 meters, then 20, then 45, then 80, and finally 125 meters at 5 seconds. Now there's another way to think about this that might surprise you. The universe doesn't have any kind of memory, so a ball that has fallen for 1 second doesn't know that the next second it's supposed to fall another 15. So here's the deal. You can sort of restart the problem at the end of 1 second, and what do you have? You have a ball that is 5 meters down, it's moving at 10 meters per second. So in the absence of gravity, it would move an additional 10 meters. Add gravity, and it falls an additional 5 meters, as if that's the new first second of free fall. Now, when you go to the next second, the exact same idea. It doesn't know that it's been falling for 2 seconds. It's got a velocity of 20 meters per second, so in the absence of gravity, it would go 20 additional meters. But gravity makes it fall from where it would have been by another 5 meters in 1 second. So it goes an additional 5. So that's 25 more meters in that second. And so forth. Each second, it falls 5 meters below where it would have been the second before. And that's really key for understanding how gravity works. What gravity does is it causes objects to fall below where they would have been if there wasn't any gravity. Let's look at a couple of other examples. Without gravity, a ball launched straight upward at 100 meters per second, that's very fast, would continue to move upward 100 meters every second in a straight line. Add in gravity and it will rise 100 minus 5, then 100 minus 20, then 100 minus 45, and so forth until it reaches a velocity of 0, at which point it will begin to fall downward as if it were dropped from that maximum height. Now let's look at a ball thrown sideways. In the absence of gravity, if we throw the ball at 10 meters per second, it's going to go in a straight line. With gravity, it's still going to move in a straight line sideways, but it's going to fall below that line vertically according to d equals 1/2 at squared. If you were on the ground below moving at 10 meters per second in the same direction, you'd see it fall straight down right on top of you, as if neither one of you were moving horizontally. This even works for a ball launched at an angle. Let's launch this one at 10 meters per second sideways and 10 meters per second upward at the same time. With no gravity, you get a straight line just as you'd expect. Add gravity and the ball falls below that line. By the way, this works in real life too. If I launch and drop a ball at the same time, they both hit the ground at the same time because they're both falling downward at the same rate, regardless of their sideways motion. So there you have it. Gravity makes things fall. I know that's not very revolutionary, but there it is. What is surprising is that when an object is moving up in the air, if it's being impacted by gravity, it's still technically falling in the most general sense of the word. It's falling below where it would be if there were no gravity. We define free fall as any time only gravity is acting on an object. And so anytime something is in free fall, it's falling. When you kick a ball, it's falling even on its way up, technically. So in our next set of videos, I'm going to go through a couple of specific examples of how you can apply the kinematics equations to these various situations that you saw here. It's really not that hard as long as you keep a couple of key ideas in mind. See you next time.